Alright, this is the third video on improper integrals. So we're going to look at two examples. We'll go through the definition here of another type of improper integral. And these are integrals with infinite discontinuities. If f is continuous on the half open or half closed, closed at a, open at b, with an infinite discontinuity at x equals b, then the integral from a to b of f of x dx is defined to be, and we're going to be approaching the infinite discontinuity b from the left side. So that is the limit as c approaches b from the left side, the negative side of the integral from a to c f of x dx. The second case is if f is continuous on open at a and closed at b with an infinite discontinuity at x equals a, then the integral from a to b of f of x dx is going to be equal to the limit as c approaches a from the positive side of the integral from c to b of f of x dx. If f is continuous on the closed interval ab except at an interior point c in the open interval ab with an infinite discontinuity at x equals c, then the integral from a to b of f of x dx is equal to the limit as t approaches c from the left-hand side of the integral from a to t f of x dx, plus the limit as t approaches c from the positive side of the integral from t to b of f of x dx. So there's our closed interval, there's a and b, infinite discontinuity at c, and so we'll approach from both the left and the right-hand sides. Whoops, go back. Hold on, go back. So we'll approach from both sides. And just like previously, we'll say the integral exists or is convergent if the limit exists. And then for part 3, the third one where we have a discontinuity in the middle, both the left and the right hand limits need to exist. Okay, so if you can handle doing it from one side, then in the interiors, nothing too special. It's very similar. You just do two integrals. So let's look at example number 8, and we're going to look at the integral from 2 to 11 of 6 over x minus 2 dx. So that's going to be the limit as b approaches 2 from the positive side. So we are on the interval, so it's discontinuous at 2. We got a vertical asymptote there, and here's 11, so we're going to be approaching 2 from the positive side. So this is going to be equal to the limit as b approaches 2 from the positive side of the integral from b to 11 of 6 over x minus 2 dx, which is equal to the limit as b approaches 2 from the positive side of 6 times the natural log of the absolute value of x minus 2, evaluated from b to 11. So it's going to be the limit as b approaches 2 from the positive side of 6 ln absolute value of 11 minus 2 minus the natural log of the absolute value of b minus 2. Okay. So here's our natural log graph, natural log of b minus 2. So notice, as we approach b from the positive side, that natural log of b minus 2 is marching down to minus infinity, and so that's not good news if we wanted this integral to converge. That's going to tell us this diverges. So this is equal to 6 natural log of 9 and minus, and then the natural log of the absolute value of b minus 2, that's going to go to negative infinity, and so we have a negative and a negative, so this is going to be a positive infinity, and so this integral is going to be divergent. The graph of 6 over x minus 2 is going to have a vertical asymptote at 2, and here's roughly what the graph would look like, and I have shaded in the area that we're going to follow there, and so if this is going to converge, this has to close up faster than it did, and so this is a divergent improper integral. Okay. Alrighty, let's look at one more here for this video, and we're going to look at the integral from 0 to 3 of 1 over the square root of 9 minus x squared dx. So here the discontinuity is going to be at 3. So we have 0 to 3, and we're going to be approaching 3 from the left side or the negative side. So this is going to be equal to the limit as b approaches 3 from the left side of the integral from 0 to b of 1 over the square root of 9 minus x squared dx, which is going to be equal to the limit as b approaches 3 from the left-hand side of the arc sine of x over 3, evaluated from 0 to b. So it's going to be the limit as b approaches 3 from the left-hand side of the arc sine of b over 3 minus the arc sine 0 over 3. Okay. Now, we're okay plugging in 3. It's going to be slightly less than 3. Remember the domain of the arctangent. Arctangent of x is going to take numbers from -1 to 1 to negative pi over 2 to pi over 2. So that's its restricted domain. So if we're looking at the arc sine of x over 3, we're okay to take numbers from -3 to 3 all the way to negative pi over 2 to pi over 2. Okay, and so approaching 3 from the left-hand side, that's valid, that's within the domain, so we can talk about this. Also, if we looked at this, we couldn't exceed 3 anyways because we'd get complex numbers there, so we can look at it from that angle as well. All right, so we can go ahead and directly substitute 3 in, and so that's going to be the arc sine of 3 over 3, which is 1, minus the arc sine of 0 over 3, which is the arc sine of 0. Arc sine of 1 is pi over 2, and the arc sine of 0 is 0, and so that gives us a area of pi over 2 for this particular function. If we were to attempt to graph this, this is going to have vertical asymptotes at 3 and -3. Okay, and it's going to look something like this. Okay, and actually it's not going to look like that because I know it converges. I know that it's going to get real close to that vertical asymptote very, very close, very, very quickly, and so we actually do have a finite area trapped in here. Okay. All right. So if we kept getting closer and closer to 3 and accumulating all this area, it's going to get closer and closer to pi over 2. Alrighty, so that's it for this video. We'll see you next time.